the last session I will try to be rather brief. So in this talk I would like to say a few words about quasinormals in this spacetime, and in particular I will focus on what happens and how to know what happens in the limit of the extremal black holes. So moreover, more or less 20 years ago, there was a paper by Bertie and Kokoktas where they were investigating quasi-normal modes for Reissner-Nordström-anti-de Sitter spacetime. In particular, they were interested in scalar electromagnetic gravitational perturbations, and they were using the typical approach where one utilizes the null foliations. And the results, well, they found out that there is a problem when the charge gets closer and closer to the extremal charge, because the methods get less and less convergent. Like, it's more and more difficult to get convergent results, and it has been a problem for a long time. So our motivation was to try to use some other type of foliation, in particular hyperboloidal foliation, and to see if you are able to see what happens in this extremal limit. So it motivated us to look into the following toy model to understand what happens for the extremal black holes. So the toy model consists of 2 + 1 dimensional space-time given by this metric element. And in particular, you can see that due to a square here, this is an extremal horizon here at x equal to 0. And also we have the boundary at x equal to 1. So this is our space-time. The foliation looks more or less like this. So it's a hyperboloidal foliation. And then we are interested in this toy model in conformally invariant wave equation, which takes form of this rather simple formula. We can simplify it even further because this part can be interpreted just as some kind of potential. So we can say, okay, let us say that this potential is more or less constant. So we say that this part is just 1/4, the C is equal 1/4. And of course, we also want to have some kind of boundary conditions here. In particular, we will choose that at x equal to 1, our solution satisfies Dirichlet boundary conditions, while at the event horizon, we just want the solution to be regular. Okay, so how can we see how the quasi-normal frequencies look like in such a space-time? So there are at least 3 different approaches. The first, and probably the most simple one, is to use some numerical scheme to evolve some generic initial data and to see what happens. And the nice thing coming from this equation is the fact that one can define an energy for this equation, and it is not conserved, but the whole change of this energy comes only from the leaking through the horizon. So like it is pretty local quantity that can be pretty easily observed. So one can have pretty simple way of observing whether there are no problems with the numerical scheme. And using simple pseudospectral methods, we can see, for example, for some generic data, the following kind of behavior of some field. And one can, of course, try to find the slope of this behavior to get the decaying part of the quasi-normal frequencies. One can also fit oscillations here, and by this approach, we can get the dominating quasi-normal frequency. But here we can, for generic data, get only the dominating quasi-normal frequency. So one can utilize other approaches like Liebert method types approaches, where we just assume that our solution looks more or less like this. We plug this ansatz into our equation, and then we also extend this function u into the following series, and this is just power series with hk being some parameters. And now the question is, for which values of hk are we able to satisfy the boundary conditions. So since we want to have the boundary condition at x equal to 1, h0 must be 0, but the mathematical condition is that we want to have our solution regular at the horizon, so then it turns out that it corresponds to the following condition, and hk here are coefficients that are just given by some recurrence relation with one free parameter, and this free parameter is just this s. And in fact, this free parameter is also, when we find the value of that free parameter s giving us this condition, we have found a good quasi-normal frequency. So this is in a way quantization condition. And in fact, we can perform like how can we solve this condition? So there are several different approaches. There is a Cleaver method approach based on continued fractions, but in fact here it is good enough to just take k large enough and see what is the expression for this hk for this large enough k. It is some polynomial in S. Then we have to solve this polynomial. Of course, we'll get some more or less good values and then a lot of rubbish. So to be able to say which values are good and which are not, we have to do the same for different values of k, and we can see that there are some convergent values which are red here, and some values that converge to 0, which are blue. And these red values give us the correct values of quasi-normal frequencies. And the last approach here, which is the key one regarding this model, is the fact that due to the simplicity of this model, you can solve the equation exactly. In fact, one can write down the green function for this equation, and then it turns out that it has the following form with denominator given by this w. And now, if this w is non-zero, then everything is fine. But when it is 0, then we have a problem with green function, which means that it is not invertible. So this is exactly it exactly means that we have the quasi-normal frequency, and in fact this w is 0 when s is equal to 0, or this function is equal to 0, where lambda, this function is the elliptic k function, where lambda is given by this, and sorry, Jacobi function, sorry, and we just have to solve, for example, numerically, but also there is a lot of analytical papers on behavior of this kind of equations to get all the possible values of quasi-normal frequencies. So these are three different methods. Yeah.
So in your few slides back, you have this point rule,
yeah,
and you say that x equals 0 is extremal horizon.
Yeah.
You didn't tell us why, but we probably calculate.
Yeah, of course.
Can you put a parameter in this model so that you have non-extremal horizons and only for some value?
Yes, and that you can go to the extremality by changing this parameter, right? It's a great question. No, we haven't done it, but it's a great next step to see whether one can find maybe not this kind of model, because probably it cannot be generalized in this direction, but some other relatively simple equation that can be solved explicitly, which has this condition you are saying. Yeah. So no, here this is just the extremal horizon that can be seen just by calculating the surface gravity at the horizon. So that's all. Okay, so here we have three different methods of getting quasi-normal frequencies for this toy model, and having this, we would like to apply some lessons from here regarding the use of these hyperboreal foliations to the more difficult question, which is Reissner-Nordström-anti-de Sitter spacetime. So in particular, we'll be mainly interested now in conformally invariant scalar equation on this background. So the first thing is the parameterization that is nice to work with here. So it is good to scale everything up to location of event horizon, and then introduce the other parameter, sigma, which is defined as the Cauchy horizon. So for sigma going to 0, we get the Schwarzschild-anti-de Sitter spacetime, while for sigma going to 1, we get the extremal case. And in this parameterization, also the cosmological constant is taken here as lambda, and in this parameterization, the metric function takes the following shape. And then the important thing is the choice of foliation. As I said, usually people were choosing the null foliations, but here we would like to choose hyperbolic ones. And then we have much more freedom how to do it properly. We can do it in many different ways. So we would like to do it in such a way that the equations that we will get after in this foliation, that these equations in this limit behave well. So usually, if one chooses some foliation in a random way, this limit is pretty bad behaving regarding the final equations. So it has to be chosen in a very particular way to obtain equations that are nice both for regular and extremal cases. We compactify the spatial domain also, so it is the Penrose diagram is very similar to the one we had for toy model. And finally, it is not necessary, but we can use also conformal invariance to simplify our equation even more. And of course, we get equation like this with some pretty complicated coefficients, but they are complicated only in an algebraic way. There are absolutely no problems with singularities or anything like this in these coefficients because we chose the time slicing in a proper way. And then, what can we see? We can perform similar experiments as before, but for different values of sigma. So for sigma equal to 0, which corresponds to Schwarzschild-anti-de Sitter spacetime, we also do something like Liber method, and see how the zeros of h case change as k, or rather m here changes, and we can see that we have a nice convergence to several values which correspond to quasi-normal frequencies. Now the more interesting thing happens when we take sigma equal, for example, 1/2, because then we have two different families of behaviors. One of them is exactly the red curves, which again corresponds to quasi-normal frequencies that have non-trivial, both imaginary and real part, but then appears also a family, which is blue here, which corresponds to zeros which are purely real. So they correspond to purely damped modes without any oscillations. And while this sigma goes to 1, one can see that this family of blue curves starts to be, one can say, either divergent or maybe convergent to 0. And we have a very similar picture, as can be seen in our toy model, suggesting that in this case, these damped modes completely disappear, purely damped modes. And it leads to some other interesting observations that here at this plot one can see the dependence of the real part of the three highest oscillatory modes and three highest purely damped modes, and how they depend on sigma. And for some value of sigma, let's say here, the highest one is red one, which is oscillatory, and in fact, in simulation, one can see, in the calculation, one can see that we have purely quasi-normal like behavior, while if we increase sigma a little bit, we can see that the blue mode, which is the purely damped mode, is now higher than the red one, which means that this oscillatory mode is damped faster than the purely damped mode. And in fact, from some generic initial data, we can see that in the beginning we have, again, purely oscillatory behavior, but then this blue mode starts dominating over the initial red one, and we have purely exponential decay according to this value here. So that is an interesting, in some way, phase transition or something like this for some value of sigma. And in the end, of course, I have started with the work by Berti and Kokotas, when they were investigating the perturbations of Reissner-Nordström-anti-de Sitter, but I was speaking mostly about conformally invariant spiral equation. However, one can use all of these things I have been talking about to study more complicated things like these perturbations just by using the same methods for the following equation where the V is a potential depending on what type of perturbations I'm interested in. And in fact, these two plots are the continuations of the plots I have shown on the first slide, but while the plots were finishing at 0.6, using these methods we are able to go up to 1, so along the whole spectrum of possible values of sigma. And that's all I wanted to say. Thank you very much for the attention.
Okay, thank you very much for your talk. Are there any questions, comments? One question.
Thanks. Can you hear me? Good. So you showed this plot with the red lines and blue lines and then the crossover.
This one?
Yes, exactly. So is anything special happening exactly at the point where the red and blue cross, where both of these oscillating and non-oscillating all of the same way?
Yeah, it's an interesting question. Well, it's difficult to say because it's like you would have to be spot on, and a little bit left you get oscillations like this, a little bit right you get something like this, but this can go very far right. So I don't know if there is anything interesting happening there, and it will be probably difficult to look at it numerically. Okay, thanks. But it's an interesting question.
More questions? If not, let's thank us.